So at the end of the last video, we saw this theorem that I have up here at the top of the screen, which is that the derivative of the function e to the x is actually just e to the x. This is a really weird idea, but it's really, really awesome that it works out that way. So let's go ahead and just take a look at one final example to kind of end this particular section. Let's see what we have here. I'm going to suppose that I'm working with a function that's negative 2x plus e to the x. I have no idea what this function looks like, but it doesn't really matter for this question. Let's take a look here at part A. Can I find f prime of x? Well, I should be able to do this now very quickly, even without going through the big scary limit, because I have several different derivative rules that I can use to help me. So one of the rules that we've established in this section is that if I have two different formulas being added together, I can take the derivative of each one of them. So I'll start by taking the derivative of negative 2x to the first. So notice I could leave the negative 2 alone, multiply it by the 1 that's going to come down from power rule, and then lower the power by 1, which would give me x to the 0. Ultimately, what we can see here is that really any time that I'm going to be taking the derivative of x to the first power, the only thing that's ever going to be left is really just the coefficient, right? Because I'm always just going to be left with an x to the 0, but x to the 0 always just turns back into the value of 1. So here I'm going to get negative 2 plus, and now I need the derivative of e to the x. But as we just saw up above, the derivative of e to the x is just e to the x. So here's my derivative. Now let's take a look at part B. At which points on this curve, determined by f, is there a horizontal tangent line? Okay, so first I have to think here. If a tangent line is horizontal, what does that tell me about it? Well, if I was thinking about a picture, a hypothetical picture of a function, I know that horizontal tangent lines are going to occur when my tangent line is flat. That's what horizontal would mean, right? And of course, tangent lines that are flat have slope 0. Okay, but notice here that I'm not interested in finding in this question the equations of those tangent lines or anything. I'm just curious at which points on this curve. So like, what is this point? Like, what are its coordinates, right? Where that tangent line actually ends up being flat. And there might be one point, there might be multiple points, I'm not sure. I want to find all of them. Okay, so I can start to think about a strategy. I know the following, and I'll write this out. I'll say, we know a horizontal line must have a slope of 0. So we want to find all values of x that make f prime of x turn into 0, because f prime of x computes the slopes of my tangent lines. So what we really want is to find all x's that make f prime of x equal to 0. Now the only way that that could happen is if negative 2 plus e to the x turned into 0, right? Like if there was a value of x that made this work. But of course, I could start to solve for x here by maybe adding 2 to the other side, and then by taking the natural log of both sides, I could see that, if x is equal to the natural log of 2, then my derivative will have a slope of 0. Perfect. Or my derivative is 0, so my tangent line has a slope of 0. So what I have here then is I found one point, and really only one point, that had natural log of 2 as its x-coordinate. But since I want the points, I would still need to find its y-coordinate. So I'll say we see that if x is equal to the natural log of 2, then f of the natural log of 2 would allow me to get a y value. So I'm going to go up here, and this would be negative 2 natural log of 2. And if I do plus e to the natural log of 2, again, some things can simplify. I'm going to get negative 2 times natural log of 2, and this here just simplifies to 2. So here is my y value. I have an x value, and now I have a y. So I can write the following conclusion. The only point at which there is a horizontal tangent is the x-coordinate is natural log of 2, and the y-coordinate is -2 natural log of 2 plus 2. Again, keep in mind that these values here are exact values, and I'm always going to require that we write things as exact values. You would not want to go to your calculator and actually go ahead and type in something like natural log of 2 and then write down 0.693. That is not exact, that's rounded, and so that would not be okay. So it's very important to make sure that we're always leaving values again as exact values. But that completely wraps up part B of our question. Notice that questions like this are going to start to become more frequent, where I'm going to ask you not just to calculate a derivative, but to demonstrate that you understand what a derivative is and how to use it. And again, you might have to write some sentences out to kind of explain your thought process and what you're doing as you do it.